Hello, my name is Youngjun. I'm a PhD student in the Ocean Science and Engineering program at Georgia Institute of Technology. I'd like to talk about our ongoing flood modeling for coastal urban regions. We are currently focusing on Tybee Island, one of the barrier islands near Savannah in Georgia. Let me first begin with introducing the compound flooding in coastal urban areas. There are multiple flooding drivers at different time scales. The short-term drivers include hydrologic drivers such as precipitation and river discharges. And from the ocean interface, there are tides, waves, and storm surges. In the long term, climate change plays an important role in not only pushing up sea levels and groundwater tables, but also modifying the hydrologic water cycles, for example, precipitation. Also, in an urban area, the stormwater drainage system influences the degrees of flooding. These flooding components often coincide during a single flood event, so vulnerable coastal communities need to understand their roles and interactions in order to prepare for future flood events. For Tybee Island, as you can see in these right two figures, it is projected that the sea level rise can cause additional inundations, not only along the coastlines, but also in these yellow colored areas through hydrologic connections, such as canals or drainage. So using a numerical modeling framework, we want to understand these different drivers in a compound flooding event under various climate change scenarios. So we are setting up one of the hydrometeorological modeling frameworks for our application to coastal urban inundation. The base model code is developed by one of the research group in National Center for Atmospheric Research and has been deployed for national water model for the nationwide stream flow predictions. As this model code is open to the public, and I think it has good physics engines for hydrology, so we have employed this model as our base model framework, and we have extended it further for our local scale flooding applications. In our model, once taking the land surface model input, such as elevation, land use, soil texture, and so on, it allows to take water levels along the coast and tidal rivers or creeks. The water levels can be from any of the regional scale computations or observations, such as smart sea level sensors. Then the land data simulation, including the high resolution precipitation, are used to provide forcing for our model, which is coupled with another engine to solve the stormwater drainage system. Therefore, our model is basically able to resolve some of the physics that are involved with precipitation, groundwater, and stormwater drainage system, as well as open water levels. These are the example simulations in 10-meter resolution during Hurricane Matthew in 2016. I'd like to note before playing the video here that in the left figure, you will see the precipitation rate. In the middle, the water depth above the ground that we are actually experiencing as inundations. And in the right, the groundwater table depth below ground. So 0 means that the soil layers up to ground are full of water, while some positive value indicate the soil layers are not yet fully wet. So you can see the storm tide water cycle in the middle figure and the flash intensive precipitations in the left figure. Also in the right figure, the soil moistures change over time as the soils absorb water from the ground. At the most flooded instance, there were high storm tide with intensive rainfalls which was causing the extensive inundations in these low-lying areas and having the soil layers fully saturated in most areas except for the high elevation areas in Tybee Island. So let me briefly mention some flooding physics that our model can demonstrate. As the water levels rise, it spreads over these red-colored inland areas that were initially dry. This is essential to model coastal inundations by tides and storm surges. Consequently, the soil layers in these yellow-colored areas become saturated by the water coming from the ground and additional subsurface flow migration. For us, this might be a good research question on how groundwater affect inundations under different sea level rise scenarios. Also, in a more local scale, once the water flows over the banks, as you can see in these red circles, the water flows into the low-lying areas and infiltrate into the soil layers. Then the flooded water drains slowly over time as the soil layers are already full of water, like in these blue circles. These physics are also important for flooding due to intensive or prolonged rainfall events. Although the stormwater drainage system is designed to drain the flooded water, it may not work depending on the water levels at the outfalls. This was a case for Tybee Island during 2014 king tide event. Due to the high tide at the outfalls, the salt water flowed back along the conduit and flooded inland at some junctions. The backwater preventer was installed a few years later, but it is also important for future planning to understand its capability to drain water in a certain condition. We were numerically testing it with this simple configuration with fictitious dimensions to check our coupling functions. First, we put constant but high prolonged precipitation of 30 millimeters per hour. The animation here shows the process of how the precipitation induces inundations in the low-lying areas. These two figures here show the difference in the inundation profiles without or with the stormwater drainage system. Although the test configuration are simple and made up of fictitious dimensions, we can see in these red circles a lesser bluish and lesser extent of the inundation areas in the presence of the stormwater drainage system. If we impose the high tide at the outfalls, like 2014 king tide event, without the tide gate, you can find the blue dots in the red circles, which represent the overflows at these junction locations. The sectional water elevation profile shows the blue water elevation line is higher than the green surface elevation line. The difference between them represent the overflow depth at these junction locations. However, with the tide gate setup, there would be no junction overflows in the same locations as no water can flow back through the conduit. To summarize, our goal is to understand the compounding effect of different flooding drivers in coastal urban areas and assess the dynamic flooding vulnerability under different climate change scenarios. We have been using a hydrometeorological modeling framework for our application by including tides and stormwater drainage systems. Our model has advantages in terms of narrowing a gap between existing regional scale computations or observations and local inundations that coastal communities can actually experience. Also, it will allow providing more physics-based insight to stakeholders for future planning or decision-making. We will be extensively working on calibrations or validation with available observation data such as photos or videos. So we really need input from coastal communities and you. This is all I have. Thank you for your attention. Thank you.